In this video, I will discuss the concept of fluids that are at rest. A fluid is any material with the ability to flow. A fluid has an indefinite shape. Out of the three phases of matter, solid, liquid, and gas, only liquids and gases have the ability to flow or have an indefinite shape. When placed in different containers, liquids and gases take the shape of the container they're in, and the molecules can flow past one another because they're not fixed to position. When studying fluids, there are a few important characteristics or quantities that can be measured or calculated. The first is a fluid's density. Density is defined as mass per unit volume. In the past, you may have used the symbol capital D for density, but in physics, density is given the symbol rho, which is a Greek letter. It looks like a curly P. Common density values can be found on page 256 of your textbook. If the material is unknown, then the table cannot be used. Instead, you can calculate the density using the equation m over v, where m is mass and v is the volume of the fluid. So what are the units for density? Because mass is measured in kilograms and volume in meters cubed, then the units for density are kilograms per meter cubed, which is the SI unit for density. But densities can also be measured in grams per centimeter cubed. You can convert from one unit to the other if necessary. For example, water has a density of 1 gram per cubic centimeter, which, converting grams to kilograms and centimeters cubed to meters cubed, gives 1,000 kilograms per meter cubed. The density formula has some useful variations that you will see from time to time in this unit. For example, if we rearrange the density equation to solve for mass, we find mass equal to rho times v, or density times volume. This can be useful when determining the weight of an object, which is calculated using m times g, but plugging in rho v for m, we get weight equals rho vg. Let's try an example using the density formula. What is the mass of a cube of aluminum that has a side length of 2.5 centimeters? Notice, if the density of aluminum were not explicitly in the problem, you could check on page 256 of your textbook. Pause the video for time to work on the solution. Density is equal to mass divided by volume. Have the density, and we're solving for mass, but we don't yet have the volume, so we must first find it. The volume of a cube is equal to length times width times height. Each side is 2.5 centimeters, or 0.025 meters. So then the volume, multiplying length by width by height, we get 1.56 times 10 to the minus 5 meters cubed. Plugging in the density of aluminum and the volume of the cube into our equation, we can then solve for m, the mass, and we find the mass to be 0.042 kilograms. Specific gravity is another quantity that's useful when studying fluids. Specific gravity is defined as the ratio of a density of a substance to the density of water. When we have a ratio, we divide. So the formula for specific gravity is density of a substance divided by the density of water, or rho of the substance divided by rho of water. You may be wondering what the units for specific gravity are. Because we're dividing a density by another density, the units cancel out. So the specific gravity is just a number. It's a ratio. Therefore, it has no units. Let's try a few problems calculating specific gravity. Calculate the specific gravity of lead, ice, and gold given the density values. Pause the video for time to work on the solution. In part A, we are asked to find the gravity of lead, and to find the specific gravity, we have to divide the density of the substance by the density of water. So we plug in the density of our substance, in this case the lead, and divide it by the density of water, 1,000 kilograms per meter cubed, and we find the specific gravity to be 11.3. And notice we have no units, because a density divided by a density gives us no units. The units will cancel. We can do the same thing for ice. We take the density of ice and divide it by the density of water, and you will find the specific gravity to be 0.917 for ice. Again, no units. And C, the specific gravity of gold turns out to be 19.3, no units, just a number. Pressure is another characteristic that is useful when studying fluids. Pressure is defined as force per unit area, and as an equation can be written as P equals F over A. Pressure is actually a scalar quantity. It has no direction. Units for pressure are newtons per meter squared, because force is in newtons, area is in meters squared, therefore force per area is newtons per meter squared. This is also known as a Pascal. The unit Pascal can be abbreviated as PA. 1 Pascal is defined as 1 Newton per meter squared. Some other units for pressure are dynes per centimeter squared, or pounds per inch squared, or also known as PSI, pounds per square inch. You are probably most familiar with PSI, or pounds per square inch, the common units for tire pressure. Let's calculate the pressure. A 60-kilogram person stands on 1 foot that has an average area of 500 centimeters squared. What pressure will the person's foot exert on the floor? Notice I've also given you the conversion factor to go from centimeters squared to meters squared, or the other way. Pause the video for time to work on the solution. Pressure is calculated using the formula force divided by area. In this case, force is the weight of the person, which is mass times the acceleration due to gravity, or 60 kilograms times 9.8 meters per second squared. Multiplying the two, we find the force to be 588 newtons. Plugging in the force into our pressure equation, and also plugging in the area. Notice we've taken 500 centimeters squared and converted it, so it's now 0.05 meters squared. We divide force by area, and we find the pressure to be 11,760 newtons per meter squared, or 11,760 pascals. When studying pressure within fluids, there are a few important principles or rules. First, fluids can exert pressure in any direction on an object or on itself. Considering a cube placed in a fluid, the fluid can exert pressure up, down, side to side, or really inward on the object. You are probably familiar with this. When swimming or diving to the bottom of a pool, you can feel the fluid exerting pressure on all parts of your body in all directions. Another example which highlights a fluid's ability to apply pressure in all directions is shown. When you place a straw into water, the water fills the straw to the height of the fluid. When you remove the straw, the water remains in the container, not in the straw. However, if you place the straw into the water, allow the water to fill the straw to the height of the fluid, and then place your thumb over the end of the straw and remove it, the water will remain in the straw until you remove your thumb from the end. This happens because there's both air and water in the straw. When your thumb is placed over the top of the straw and you remove the straw from the water, a very tiny amount of water is lost from the straw. Because some water leaves the straw, it causes the air above it, between the water and your thumb, to expand slightly to fill the space that the water left. This creates a low pressure area inside the straw. The more water that leaves, the lower the pressure, but only enough water will leave so that the pressure above the water and the pressure below the water are almost the same, and therefore the water is in equilibrium. When you release your thumb, air is able to flow into the low pressure region at the top of the straw, creating higher pressure and pushing the water out of the straw. It is also important to understand that fluids exert pressure perpendicular to any surfaces it is in contact with. For example, if a small ball is placed in a fluid, the fluid will exert pressure in all directions on the ball, but always perpendicular to the surface. If you submerge your body under water or within another fluid, then that fluid will always exert pressure perpendicular to the surface of your body. Also, when a fluid is in contact with a container, it will only exert pressure perpendicular to the surface of the container, into the walls of the container and to the bottom of the container, perpendicular to the surface. You may be wondering why a fluid must exert pressure perpendicular to any surface it's in contact with. Let's analyze what would happen if the fluid did not exert pressure at right angle or perpendicular to surfaces. Let's say a little bit of fluid exerts a pressure P on the surface of the container. Notice it is not perpendicular to the container. Well, because pressure is defined as force per unit area, the fluid would be applying a force on the container. So we'll now replace the P, the pressure, with F for force. This force could then be broken into components. A component perpendicular to the container and a component parallel to the container. If the fluid exerts a force on the container perpendicular to it, then the container applies a force equal and opposite on the fluid, as stated in Newton's third law. So these are action-reaction forces, and the fluid and container both remain at rest. However, the fluid would also be applying a parallel force on the container. And because there's no reaction force created by the container, the fluid would be in motion, which violates the fact that we're studying fluids at rest. So pressures must be perpendicular to surfaces in order for fluids to remain at rest. A third rule or pressure principle is that pressure varies with depth within a fluid, and we can determine the amount of pressure if given the depth. The formula for pressure at a depth can be derived from the original pressure equation. Consider a cube with a surface area A placed into a beaker of water or another fluid. Let's say we're trying to determine the pressure at a depth h, the top of the cube. Well, pressure is force divided by area, but the force on the top of the cube is due to the weight of the fluid above it. So, the F can be changed to weight, which is mg. So we have pressure equals mg divided by A. But recall from rearrangement of the density equation that mass is equal to density times volume, or rho times V. So we now have P equals rho Vg divided by A. But the volume of the fluid above the cube is the surface area times the depth h. In this equation, our a's cancel, and we're left with the pressure at a depth equal to rho gh, where rho is density, g is the acceleration due to gravity, and h is the depth. So keeping that equation in mind, consider the container shown filled with a single liquid with a given density, and each column having a different shape. Which point at the bottom of the container, A, B, or C, has the greatest pressure? This was actually a trick question, because each column is filled with the same fluid to the same height or depth. The pressures will be the same, because pressure is rho GH. Even though A has more fluid in that part of the container, it's not the amount of fluid that determines the pressure, the depth of the fluid. B has a little funky shape to it, but still has the same depth under the fluid. And although C is skinny and has a smaller amount of fluid above it, again, it is the same depth below the fluid as A and B are. So they actually all have the same pressure at the bottom of the container. I have seen this as a previous AP multiple choice question. Finding a single pressure at a given depth can be important. It can also be useful to determine pressure differences between two different depths on an object. Consider a beaker full of a single fluid, and we're going to take a look at just a chunk of that fluid inside, a cube shape. And as I just described, the pressure at a depth is equal to rho GH, so the deeper in the fluid, the more pressure there will be. So there will be some fluid pressure pressing down on the chunk of fluid, and because the bottom of the chunk of the fluid is at a greater depth, the pressure will actually be greater underneath the chunk of fluid. But that's interesting too, because if there's a pressure difference, then shouldn't the fluid be in motion because the pressures aren't balanced? Well, don't forget, the chunk of fluid also has weight. So this creates more downward force to cause all of the forces or pressures to become balanced. So the chunk of fluid would in fact be at rest, in equilibrium, which is consistent with our study of fluids at rest. So then how do we calculate a pressure difference? Well, now the fluid is at rest, so the net force is 0 on this little chunk of fluid. We can see each force as well as their action in the equation. So we have force that's created at the bottom minus the force at the top minus the weight. And we have a positive, in this case, being considered upward. So we have an upward force and two downward forces. One positive force and two negative forces. Well, the upward force is going to be equal to pressure times area, but it's a pressure plus a difference in pressure caused by the depth times the area. For our second pressure, or second force on top, we have force equals pressure times area, and the surface area is A and the pressure is P. And then we have this third and final force, which we say is the weight, mg, but M is rho Vg, and V is area times h. So in this case, the weight is equal to rho A delta H times G. Plugging in each of these forces and their equations, and then doing a little bit of algebra, we can distribute the A into the parentheses, and we get PA plus delta PA, that's force at the bottom, minus PA, which is the force at the top, minus rho A delta HG, which is the weight, and then set that equal to 0. Well, notice our PA's cancel. We have a positive PA and a minus PA. They cancel each other out. And moving the equations to opposite sides, we find delta PA equal to rho A to HG. But we have an A on both sides of the equation. Can get rid of that, so delta P, the change in pressure, or difference in pressure, is equal to rho G delta H, where delta H is the difference in depths. And delta H can be rewritten as H2 minus H1, or the deeper depth minus the shallow. So delta P equals rho G delta H, or delta P equals rho G H2 minus H1. The atmosphere is a fluid, so it also has the ability to exert pressure on objects. We call this atmospheric pressure, or pressure due to Earth's atmosphere. Air pressure, or atmospheric pressure, is the pressure due to the weight of the fluid or the atmosphere above a given point. For example, at sea level, the atmospheric pressure is 14.7 pounds per square inch, or 1.013 times 10 to the 5th newtons per squared. This means when you're standing at sea level, for every square inch of area on your body, you feel 14.7 extra pounds because of the fluid or the atmosphere above you. Our bodies are structured in a way that we can withstand this amount of pressure or extra weight added on our bodies. Another unit of pressure is defined as an atmosphere. 1 atmosphere is defined as 1.013 times 10 to the 5th newtons per meter squared, or 101.3 kilopascals. The idea of atmospheric pressure and pressure at a depth is very apparent in the picture shown. At sea level, there's a huge column of air above, so the weight of that entire column of air is applying pressure. However, the higher you climb in elevation, the less air or atmosphere is above you. Because there's less air, then the weight of that air is less. Therefore, the atmosphere above is not applying as much pressure. And this is very obvious, but if you're at the top of the atmosphere, then there's no atmosphere above you applying pressure. So the atmospheric pressure at the top of the atmosphere is 0. To measure atmospheric pressure, we can use a device called a mercury barometer, which consists of a container and a tube filled with mercury. At the top of the tube is a vacuum, where the air pressure is 0. Because the container of mercury is open to the atmosphere, or the fluid outside, it can apply pressure on the mercury. If air exerts more pressure on the mercury in the container, then it pushes the mercury in the container down, which will cause the mercury in the tube to rise. Because the pressure beneath the mercury plus the atmosphere in the container must be equal to the pressure beneath the mercury and the vacuum in the tube. Otherwise, the fluid would be in motion. If the air outside applies less pressure on the mercury in the container, then the level of mercury will fall to match the pressure on the container. Barometric pressure is measured in millimeters of mercury, which is the height of the column of mercury in the tube. Atmospheric pressure, or 1 atmosphere, results in a height of mercury in the tube of 760 millimeters. So another unit used sometimes for pressure is millimeters of mercury. 1 atmosphere can also be considered a pressure of 760 millimeters of mercury. Gauge pressure is another useful measure when studying fluids. Gauge pressure, for example, is the pressure that is measured in a tire. Consider a tire filled with air. There's an external pressure on the tire caused by the air outside, the atmosphere, and there's an internal pressure caused by the air inside the tire. A tire gauge would read the pressure above and beyond atmospheric pressure, which means it only reads the internal pressure, the pressure caused by the fluid inside, pressing back on the gauge. But if you're interested in the total pressure on the tire, also known as absolute pressure, then you would take the internal pressure, the gauge pressure, and add it to the external pressure, atmospheric pressure. Let's try an example. What is the absolute pressure, A, in pascals, and B, in atmospheres, at the ocean floor 3,800 meters beneath the surface, where the Titanic wreckage lies, if the density of seawater is 1,020 kilograms per meter cubed? Pause the video for time to work on the solution. In part A, we're asked to find the pressure at a depth in pascals. Well, pressure at a depth is gauge pressure, which is rho GH. The density of seawater is given. G is 9.8 meters per second squared, and the H, or depth, is 3,800 meters. Multiplying those, we find the gauge pressure to be 38,171,000 pascals. But we want the absolute pressure, not the gauge pressure, so we have to add atmospheric pressure to the gauge pressure. Atmospheric pressure is 1.013 times 10 to the 5th pascals. Add that to our gauge pressure, and we find 3.83 times 10 to the 7 pascals as our absolute pressure. Part B asks us to convert that pressure in pascals to a pressure in atmospheres. Well, 1 atmosphere is 10 to the 5th, or about 10 to the 5th pascals. So we divide our absolute pressure by 10 to the 5th, and we find the absolute pressure to be about 383 atmospheres. Here's another example. Water and then oil are poured into a U-shaped tube, open at both ends, and they do not mix, as shown in the diagram. Find the density of the oil. Pause the video for time to work on the solution. As shown in the diagram of the U-shaped tube, A and B must be at the exact same pressure in order for this fluid to remain at rest. So B is exactly at the bottom of the oil, and A is directly across from it in the other side of the U-shaped tube underneath the water. Notice, the water's height is different from the oil's height because they have different densities, but the pressures at these points are the exact same. So PA is equal to PB, and pressure at these depths is rho GH. So A is underneath the water, so we have density of water times G times H of the water, the depth of the water, equals rho GH for the oil at point B. We can plug in our values. We have the density of water, G, and H of the water. H of the water is 15 centimeters minus 5 centimeters from our diagram. Density of oil, on the right side we don't know, times 9.8 meters per second squared times 15 centimeters, which is the height of the oil, and we can begin to solve for the density of the oil. And we find it to be 667 kilograms per meter cubed. One more important principle in studying fluids is known as Pascal's principle, which states that if an external pressure is applied to a confined fluid, and an enclosed fluid, the pressure at every point within the fluid increases by that amount. So if you apply a pressure at one side of the fluid, then that pressure has to increase throughout the entire fluid by the same amount. For example, consider a car lift. We apply a force, F1, at our first point, piston, and that piston applies a force or a pressure on the fluid inside that enclosed container. Because there's a pressure on that side of the container, then the pressure inside the fluid must increase by that same amount throughout the entire fluid, and therefore will apply a pressure or a force on the other piston at point 2 and lift a car. But how could a person apply a force on one end and have the second piston apply a force enough to lift a car? Well, that's because of the difference in area. Because the pressures must be the same at point 1 and point 2, then a small force over a small area will result in a large force over a large area. So because area 2 is much, much bigger, then force 2 will be greater in order to keep P1 and P2 the same. One practical example which highlights Pascal's principle is a car brake system. When you press on the brake pedal, there is a piston attached to it which applies a pressure on your brake fluid. And that increase in pressure is transmitted throughout the entire fluid, and the fluid then applies pressure on pistons which have your brake pads attached, and this will cause you to slip. So there has to be a fluid in order to transmit that pressure. If you don't have enough brake fluid, or there's a leak in your brake fluid, then that pressure cannot be transmitted throughout the entire fluid, and your brakes may not work. So it's important to have that brake fluid in your brake system. Another example that highlights Pascal's principle is the hydraulic pistons that are used in heavy machinery like an excavator. You can see the little pistons in the picture. A final example that highlights Pascal's principle is the braking mechanism in bicycles. You apply a pressure to the handle brake, and the pressure is transmitted through a fluid through the tubing, and the brakes are applied to the wheels. So without that fluid, you would not be able to transmit that pressure to apply the brakes. Here's a problem involving Pascal's principle. In a hydraulic lift, the diameters of the pistons are 0.1 meters and 0.5 meters. A car weighing 12,000 newtons is to be lifted by the force of the large piston. Part A, what force is to be applied to the small piston? And Part B, when the small piston is pushed down by 0.02 meters, how far is the car lifted? Pause the video for time to work on the solution. According to Pascal's principle, a pressure at point 1 is equal to a pressure at point 2, or anywhere throughout the fluid, but pressure is force divided by area, so F1 over A1 equals F2 over A2. But area of a piston, or a cylinder, is going to be pi r squared. F1 is the larger piston, so 12,000 newtons is the weight of the car on that piston, divided by the area of that piston, so r squared. Set that equal to the force 2, which is what we're looking for, divided by pi r squared of that piston. Do a little algebra, and we find the force to be 480 newtons. For part B, we want to figure out how far the piston moves. So we take the volume of the fluid pushed down by the small piston and set it equal to the volume of the fluid up by the large piston. Because the volume of the fluid doesn't change, it's incompressible. So, volume is area times height or distance. So A1 x1 equals the volume of the large piston, A2 x2. Plugging in our areas and our distance 1, we can solve for distance 2. We find it to be 0.008 meters.